Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 9th, 2026, just yesterday. It introduces a post-training method that leverages a model's own historical weaknesses to break through learning plateaus, boosting accuracy on the difficult AIM 2025 benchmark from around 12% to 20%. The paper is titled Weak-Driven Learning: How Weak Agents Make Strong Agents Stronger. And as we'll see shortly, the results are particularly impressive because they require zero additional inference cost. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the paradigm shift this paper proposes. The top left panel depicts standard distillation-based learning, where a powerful teacher transfers knowledge to improve a weaker student. In contrast, the bottom left shows weak-driven learning, which flips this flow. A weak historical checkpoint provides corrective signals to an already strong model, pushing its average performance from 61 to over 69%. The radar chart on the right confirms this gain, showing the red line for the new method extending beyond the blue baseline across benchmarks like Math 500. Figure 2 details the full pipeline, breaking it down into 3 distinct stages. In stage 1, shown in the top left, the process starts with 2 models: a weak agent, which is a historical checkpoint, and a strong agent derived from standard supervised fine-tuning. Moving to stage 2 on the right, the framework uses Entropy to compare these agents, selecting specific active data where the strong model shows signs of forgetting or instability. Then, stage 3 at the bottom left performs the actual training by fusing the logics from both models. The chart on the bottom right explains the intuition here. By mixing in the weak model's less confident predictions, the system preserves hard negatives, plausible but incorrect options, which prevents the strong model from becoming overconfident and stopping its learning too early. So, Figure 2 explained the mechanism. Now, Table 1 presents the main performance gains. Here, the authors benchmark WMSS against standard supervised fine-tuning and other noise-based methods like NEF-tune. The results on the QN34B model are particularly striking. Looking at the hard AIM 2025 math benchmark in the first column, accuracy jumps from roughly 12% with standard tuning to 20% with WMSS. This trend holds for larger models too. The QN38B model sees its average math accuracy climb from about 67% to nearly 73%, confirming that these gains scale effectively. So, while Table 1 highlighted the final accuracy, Figure 3 tracks the training dynamics for the QN34B base model across 7 datasets over 4 epochs. The plot reveals a clear pattern: rapid learning in the early stages, followed by stabilization. You can see this in the red line for the difficult AIM 2025 task, which climbs steadily from near 0 to 20%. However, the orange line for AIMC 2023 serves as a warning. It peaks at Epoch 3 and then regresses. This drop in the shaded convergence zone illustrates why the authors stop training before catastrophic forgetting sets in. Alright, Figure 3 showed the performance plateau, and Figure 4 now explains the underlying mechanism using the QN34B model. The solid teal line tracks the target signal strength, which rises rapidly before hitting a ceiling labeled signal saturation. At the same time, the dashed red line shows the distractor level, the scores for incorrect answers, dropping and then leveling off. The large shaded area on the right marks the stagnation phase. Since both the correct and incorrect signals stop changing here, the model effectively stops learning, which is the specific bottleneck this paper's method is designed to break. Well, Figure 4 identified the saturation problem, and now Table 3 deconstructs the solution to see what actually works. The first row sets the baseline with an average accuracy of roughly 54%. The second row shows that adding curriculum-enhanced data activation yields a modest gain to 56%. The third row indicates that joint training of weak and strong is more effective, lifting performance to 58%. However, the last row shows that combining both into the full WMSS framework achieves the highest robustness, doubling the score on the hard AIME benchmark to 20%. Wrapping up, the big hook here is that models can self-evolve by repurposing their own past mistakes, breaking the saturation bottleneck without expensive teacher models. This method delivers sharp gains on complex tasks like AIME 2025 while adding zero cost to inference. It turns out that a model's history is actually a rich source of supervisory data. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.